Before the chemical potential energy of gunpowder was discovered, people who wanted to mercilessly kill each other over long distances had to use a little bit of physics in order to hit their mark. Whether used for hunting, human annihilation, or sport, the bow and arrow was almost always the most efficient weapon of choice. Archery has been dated back to 20,000 BC and was used in numerous wars such as the Egyptians versus the Persians. Other variations of this famous weapon include the crossbow, a horizontally mounted bow equipped with a trigger for easier aiming. That one was pretty awesome too. Using any ranged weapon, whether it be the modern day sniper or a piece of wood and string, requires a slight understanding of physics.
The average bow and arrow consists of a pair of curved elastic limbs traditionally made from wood. These limbs are tied together by a bowstring which was usually made from linen or hemp. When the string is pulled back, both a compressive force exerted on the limbs and a tension force on the string is created. This design allows the archer to store a large amount of potential energy in the bow. The archer also can tell that by pulling back harder on the string, more potential energy is stored, making the shot more powerful. This is known as the draw weight, which cleverly allows the archer to know how hard to pull back when making their shot. A traditional arrow consists of 4 major parts. At the back end of the arrow we have the notch, which allows the archer to place the end of the arrow onto the string more securely. The fletchings are added in order to make the arrow more stable during flight. The shaft is a long, slim piece that is usually made from wood, aluminum, or carbon fibers. At the deadly end of the arrow, we have the arrowhead. These are traditionally made from flint, bone, or horn, but are nowadays usually made from metal. As you can see, the bow and arrow is truly innovative for its time. And if you ever get caught at the end of this projectile, you're gonna have a bad time.
This is our archer. Let's call him Chief. Chief's getting real hungry. He needs to rustle up some grub real fast so he can bring it back to his tribe. Problem is, he doesn't know how to shoot an arrow. Let's see what's wrong.
One of Chief's problems might be that he isn't pulling back far enough on the string. Using a projectile motion chart, we can derive the equation for the horizontal distance achieved by launching the arrow. We went on to conduct 2 trials to test the effect of the pullback or deformation of the bowstring on the initial velocity of the arrow. In trial 1, Chief pulls back with a 0.12 meter deformation and the initial velocity was calculated to be 10.8 meters per second. In trial 2, Chief pulls back with a 0.32 meter deformation and the initial velocity was calculated to be 19.8 meters per second. So we can conclude that the farther that Chief pulls back on the string, the more velocity is given to the arrow upon launch. We also know that work equals force times distance, the distance in this case being the deformation on the bowstring. The more work that is put into the bow, the more kinetic energy is given to the arrow because energy is conserved. In trial 2, more work was done on the bow, therefore the arrow went faster.
However, Chief can still get this arrow to go even farther. This is because Chief is not shooting the arrow at 45 degrees. Using the equation we derived earlier, we can see that a 45-degree launch angle will allow for the greatest horizontal distance. In trial 3, Chief shot the arrow at this angle to achieve a greater distance than both the previous trials. So as we can see, a 45-degree angle is ideal for maximum horizontal distance.
Because of humanity's innate curiosity, Chief decides to shoot a different arrow. This arrow is rectangular with a square end of 1.5 centimeters. The equation for drag is the drag coefficient times the reference area times 1/2 times the air density times velocity squared. The drag coefficient for a rectangular arrow is 0.82 and the velocity was a slow 9.2 meters per second. We calculated the drag to be 0.01007 piconewtons. The streamlined arrow had a drag coefficient of 0.04, and if shot at the same velocity, the drag would be 6.86 to the negative 6 piconewtons, which is a lot smaller than the bad arrow's drag.
Thanks to our expert testimony, Chief is now ready to violently skewer some innocent animals and feed his tribe with his well-earned meal. But uh-oh, is that the white man I hear coming? Oh man, it looks like it is. I guess we'll catch you later, Chief.